Hello, welcome to this video. What we're going to do today is we're going to go through two FRQ questions that sort of sample from some new topics, some old topics. Should be a good kind of well-rounded review of a lot of stuff. All right. So I don't have the printed handouts. I probably didn't give them to the sub, but you guys can just take some notes on a loose leaf sheet of paper. But we're going to go through problem 4, and we're going to go through problem 5. So it should be some kind of nice stuff. Okay. So part A, on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. All right, so we have this differential equation that should basically help us make a nice little slope field by plugging in these points. And let me just maybe I'll start at the origin and go sort of clockwise, right? Remember, this is, 0, 0, 0, 1, 0, 2. The mistake you're most likely going to make is you're going to switch the x and the y and get the wrong slope. So just make sure you're being careful. But I'll plug in 0 first. So for 0, 0, I get a slope of 0. Right, so that's going to be a horizontal line. For 0, 1, we get this. Looks like we get -1 for the slope there. -1 slope looks like that. For 0, 2, we get -4. Slope looks like that. For 2, 0, so we get 0 squared over 2 minus 1. It's going to be 0, so another 0 slope there. For 2, 1, we get 1, slope of 1. For 2, 2, we get 4 over 1, it's positive 4. So in general, right, this is sort of what you should have. I think on the scoring guidelines, they essentially just look to make sure that you have these, why does it keep switching to eraser? They essentially just look to make sure that you have those 0 slopes, and then they check that these are non-zero slopes. And I think that's all they really look at, according to the scoring guidelines. I'm not an AP reader, but that's what it said. So essentially, you would get probably, I think, two points for that part A. The other parts have a lot more points with them. So part B, let y equal f of x be the particular solution to the given differential equation with the initial condition of f of 2 equals 3. They ask us for two things here. Write an equation for the line tangent to the graph of this, the particular solution at x equals 2, and then use your equation to approximate f of 2.1. So let me get into that first request that they ask of us. So why would we even want to do this in the first place? Well, when it comes to graphs that tend to be kind of complicated, that may have some natural logarithms and other things like that, tends to use a lot of computing power to get those outputs. And so to save on computing power, what a lot of softwares essentially do, because it's pretty much just as good, is, let's say this is just some complicated curve. I know it doesn't look like it, but let's just assume that the equation there is very complicated. And we have 2, 3 is, let's say, this point right here. What computers will often do is, instead of actually going to 2.1 and trying to find the output there, they'll actually instead make an approximation, right? So they'll say, okay, what is the tangent line? So I'll do that maybe in red, to this specific curve at that point or near that point. And instead of plugging 2.1 into the function, it will actually plug it into this tangent line. And, in general, right, that output, it's not going to be the right answer, but it's going to be close enough for most things that you're trying to do. So that's the idea here. It's actually a very very popular and often used trick that computers and programs and softwares are constantly doing in the background of whatever we're trying to do. So anyway, that's why you might want to do something like that. So let's just do part B, right? Well, we're not solving the differential equation. That's going to come in part C. We just want the equation of that tangent line. So we already have a formula that spits out the derivative or the slope of the tangent line at any point. Right? It's an implicit derivative, but it can still work. Right? So what we might say is dy dx at x equals at the point 2, 3. Right? That's how you would actually write this in mathematical notation. We would say that this is equal to 3 squared over 2 minus 1. And it looks like that gives us an answer of 9. So 9 is the slope of this tangent line we're trying to find. Obviously, that's very different from my picture. I just made up a curve, right? I just made one up. So obviously, it should be different too. But the slope of the tangent line we're looking for is 9. So m equals 9. And it goes through the point 2, 3. Well, if you're writing the equation of a line, and you got a point and a slope, you best believe we're going to use point slope form. Y minus 3 equals 9 times x minus 2. Point slope form is so easy. Just use it, right? Slope intercept form, not as good. So anyway, let's go ahead and clean this up here. We get y equals 9x minus, minus 18 plus 3 is minus 15, right? So this is the equation of the tangent line. They would probably give you some points for this slope, maybe for the equation of this line. And then at the end, right, we want to approximate f of 2.1. And the approximation is just going to come from this tangent line. So we're going to plug 2.1 into the right side of that tangent line there. So this is equal to 18.9 minus 15. That's going to be 3.9. So there we go. And notice too, guys, that in this FRQ section, these are the no calculator allowed for these problems section. So if you're using a calculator to follow along with me, you wouldn't be allowed to do that on a real AP test. So try to see if you can do all this stuff by hand. All right, so that's part B. Right? We did that successfully. And then part C, this is where we actually solve for the true particular solution. And once we get the answer, you're going to see why you might want to make an approximation of it. It's kind of complicated. Now, let's go ahead and rewrite the differential equation. So dy over dx equals y squared over x minus 1. And the first step we're probably going to want to do is we want to separate those variables. So I'm going to multiply by dx on both sides. And we want to get our y's on the left, our x's on the right. We already have the x's together. Let's go ahead and get that y over there. Let's multiply by 1 over y squared on both sides. All right, so this will cancel with that. And ta-da! We have now separated the variables. And in fact, if you look at the scoring guidelines, you get points for doing that. You get points just for separating it. So that's really nice. It's really nice of them. Let's go ahead and integrate. So we integrate and we get the left side turns into, it looks like negative 1 over y. The right side turns into, it looks like, the natural log of x minus 1. Of course, we got to have a plus c for the general solution, right? But they want the particular. They want it to satisfy this condition of when x is 2, y is 3, right? So we would plug in 3 for y, plug in 2 for x, and solve for that constant c, right? So negative 1/3 equals ln of 1. Oh, look at that. You guys should know what that is. That's 0, right? Ln of 1 is 0. Ln of e is 1, right? So those two on the non-calculator parts, you can see it with your own eyes. They show up, right? They expect you to know that. And so we get that c is equal to negative 1/3. But that's not the particular, right? The particular is when we solve for y and we plug in this constant, right? So let's put all this in. We get ln of x minus 1 minus 1/3. And if you look at the scoring guidelines, they do in fact want you to solve for y. They probably would not be okay if you left your answer like this. I know I let you guys do that on the last test, but for the AP, that's a no-no. So we got to solve for y. So what do? Multiply maybe by negative 1 on both sides. Right, so we get 1/3 minus the natural log of x minus 1. And then we take the reciprocal of both sides. And I know what some of y'all are going to do. And if you're thinking it's too easy, you're probably wrong, right? You take that entire right side and you flip it. So yes, you will see a fraction inside of another fraction. It's going to look like this. And yes, that is completely different than this. Well, I'm running out of room here, but if you tried to take the reciprocal of each piece separately, that's a totally different thing. It's not the right answer. You got to have it the way I have it written in red there. And so that right there, that's the actual solution to that equation. And that's fairly complicated. Like, our computers are really, really powerful these days, but that's just gonna take so many computations. Even to begin with, the natural log function, just to get those outputs takes a lot of computation. And then to top it all off, to do all this other garbage, it's just a lot better to make approximations for most things that you're trying to do on a computer. So that's why part B is not such a random thing to do. Anyway, we're going to go ahead and move on to the next one. So this one's kind of cool. Problem number 5. So we have the inside of a funnel of height 10 inches, has circular cross sections, which we can see. At height h, the radius of the funnel is given by this equation. Right, so it relates the radius to the height. You plug in a height, it spits out the radius. You want to think of that kind of like a function, where h is between 0 and 10. The units of r and h are inches. And let's just kind of get a nice little visual, right? In case that visual on paper doesn't quite do it for you. Let's go ahead and try to get a nice little visual here. Uh-oh, my program froze a little bit, but this is essentially what we're looking at. So what I did was I graphed the equation of that little radius function. Essentially what I'm doing is I'm treating the h as if it was x, right? So this x-axis, you can kind of think of it as the h-axis or the height axis. And you can kind of think of this y-axis as the radius axis, right? And it's creating this little curved funnel looking thing, right? That's kind of cool. Anyway, let's go back to the problem, right? So it says find the average value of the radius of the funnel. Now we got to think back, right? Man, these are two really good FRQs. We're covering all sorts of stuff. First of all, what is average value? That's a very important key phrase. They will definitely ask about that on any practice AP test. I can almost guarantee you, I bet my life on it. What is average value? Well, let's say we're trying to find the average value of a function f on some interval a to b, right? What's the general definition? It's the integral from a to b of f, let's say in terms of x, right? And then you also need this first part. You need to take 1 over b minus a at the beginning. So essentially what it does is you're calculating this Riemann integral. You're adding up all these rectangles, and then you're dividing by the interval you just integrated on. That's a lot of fancy words. So we want to do something like that for the radius. Right? So how do we sort of translate this over to part A? Well, think about what I said earlier, right? That you want to think of this as a function. You sort of want to think of it as a function of r of h. So h is your input. You're plugging in h. It spits out your radius for you. So if we want to find the average, if we want to find the average radius or average r, we would integrate something which is essentially the radius as a function of height. We want to integrate the radius. So we want to add up all these little radiuses at different heights. So naturally, we should have a dh here. Right? We want to add up all these radiuses. And then we want to divide by the interval we're integrating over, which in this case is from 0 to 10. It's 10 minus 0. And we're integrating from 0 to 10. Right? So just imagine, right? If you're trying to find an average radius, you're basically doing a little Riemann sum here. All these little radiuses, and then you're sort of dividing by the overall interval. Right? So it's the same idea. Now we actually have the radius function, right? We actually know what it is. So let's go ahead and put it in. So we have from 0 to 10, 1 over 20 times 3 plus h squared dh, right? That's the actual function. And now let's actually do the integral. So we have 1 over 10. In fact, I'm going to pull the 20 out. So we have 1 over 200. 0 to 10. 3 plus h squared dh. So this will be 1 over 200 times, let me do the antiderivative, that's going to be 3h plus h cubed over 3 from 0 to 10. All right, the 0 doesn't really matter in this case, so we just plug in the 10 basically. And what do we get? We get 30 plus 1,000 over 3. And again, this is the no calculator part. You got to do all this, right? All this by hand. So let's see. We get 1,090 over 3. And if you simplify this all the way, looks like we finally get an answer of 109 over 60 inches. And yes, the units are inches because remember, this is an average radius. Radius has units inches. All right, so that should be the units there. All right, cool. So let's also find the volume of the funnel as well. So the volume. This is going to be we want to treat this as a volume of revolution, right? So think about this curve being revolved around. It creates these little discs here. These disc cross sections. And we have a function that spits out the radius, right? And we basically know how these integrals work, right? We've been doing these for the past week or so. We know we're going to integrate from 0 to 10 again, All right, so we're integrating along the h-axis, integrating over h, and we're integrating dh, that's, these are the tiny widths to these disks here, times the area of each disk. And what is the area? It's going to be pi times the radius squared. And we know what the radius is. It's going to be this thing. And there we go. All right? So let's go ahead and figure this out. So we get the integral from 0 to 10, pi over 400 times, well, you know what, I'll distribute this later. I'll distribute that later. Let's go ahead and pull the constant out to the front and then distribute the parentheses there. So we get 9 plus 6h squared plus h to the fourth dh. All right. Now let's take the antiderivative. So we have 9h plus 2h cubed plus h to the fifth over 5 from 0 to 10. Now let's plug in the 10. All right. 90 plus 2,000. Let's see. 10 to the fifth power is 100,000. 100,000 divided by 5 is 20,000. All right. All right. So this turns into pi over 400 times 22,090. Oh yeah, there's no denominator, right? That's actually just the number there. And I'm pretty sure this simplifies. The only thing you can do is you can get rid of like a 0 on each of these numbers, and that's about it. So the final answer is 2209 pi over 40. And this is volume, right? So we're going to talk about inches cubed here for the units. Nice. And then, this is the best way to end this, right? Part C. You guys might read that and be scratching your heads for a little bit, but then you'll realize we learned this a long time ago. So anyway, let's just read part C kind of slowly here. So the funnel contains liquid that's draining from the bottom. Right, so let's just draw that, right? We've got liquid. The funnel's filled with liquid, and at the bottom there's a little hole, and it's spilling out of the funnel, right? So what's going on here? That's what's going on. At the instant when the height of the liquid is exactly 3 inches, the radius of the surface of the liquid, right? So that's the surface is just this top cross section here. That radius is decreasing at a rate of 1/5 inch per second. 1/5 inch per second. Now, the radius is decreasing. So this rate of change, because it's a real-world problem, they have to give you the number in terms of a positive number. But if a radius is decreasing, the rate of change is negative. So keep that in mind. At this instant, what is the rate of change of the height with respect to time? What does that sound like? How would we actually write that? We would write that as dH over dt, right? Change in height over change in time. That's what we want to find. How do we find that? You got to think all the way back to related rates. Related rates. That was chapter 3 from first semester. That seems like ages ago. What was the trick? What was the trick? Well, if you have any sort of equation that relates two variables, in other words, this guy right here, it relates the radius with the height. Very simple trick you could do. Just take the time derivative of both sides. and you do it to the entire side. So we do it to the left side and the right side. And remember, because these letters are different from our derivative, our dt, that means we have to account for the chain rule, right? So the left side is pretty easy. It's just dr over dt. And in fact, you know what I might do? I might, let's go ahead and rewrite this inner part here so it's just easier. This is 3 over 20 plus h squared over 20. When I'm taking a derivative of the right side, I know I'm going to get 0 for the first term because there's no time. It's a constant. And the next term is going to give me h over 10, right? We're doing the power rule on that second term, and then times the time derivative of h, right? dh over dt, which is exactly what we're looking for, right? That's what they want us to find. Now, how do we figure that out? Well, they give us some information, right? They tell us the radius is decreasing at this rate. That's talking about your dr over dt. And because it's decreasing, we know it's negative. So on this left side, it would be negative 1/5. What do they also tell us? They tell us at this specific moment, the height is 3. So I would plug that in for h. And bada bing, bada boom, we can solve for dh over dt. And what are we going to get? We are going to get negative 10 over 15, which is negative 2/3. What are the units for this, right? It's a rate, right? So this would be change in height, which is inches, over change in time, which is seconds, it looks like. So we have to make sure we have those units there too. But yeah, negative 2/3 inches per second. And man, that's a great one to circle back to, because looking at a lot of these FRQs over the past couple weeks, I realized there actually are a fair bit of related rates problems. So if that's something you're really rusty on, I would definitely refresh yourself, because we got one right smack dab in the middle of this random volume of revolution problem, right? So related rates is definitely the most applicable part of calculus, other than integration, I would say. So it's just a good skill to know. But anyway, I will see you guys next, I guess, on Thursday, Friday? Yeah, Thursday. I will see you on Thursday for my 3A class. 7A, I guess I'll post this and you can watch it. I'll probably go through this in class anyway. But anyway, take care. If you're having a sub for this day, they should have the next worksheet for y'all to work on. It's going to have a washer method problem, or maybe 2 of them. And then it's going to have some sort of refresher derivatives, refresher integrals, I think. Or maybe it's just derivatives, I'm not sure. Anyway, just some good stuff to review. So that will be counted as a homework grade as well. So anyway, take care. I'll see y'all next time.